So Newton-Raphson, another power flow method. It's going to lead us to the exact same endpoint, and it's going to use an iterative method. The way that it's implemented is going to be different, and we talked about it last time, so I'll go quickly through it today. Sorry, I'm pausing here for a second. Okay, so Newton-Raphson method based off of Taylor series expansion of an expression. Okay, and if we have these, let's say we have a generic constraint called G, which is a function of x1, x2, and u. And that can be split up into two separate constraints. So this is a set of constraints. These are two separate constraints. Where we have a function, some sort of a cost function or objective function, minus a constraint, static constraint. Same thing here. So the takeaway is we have a function minus a constant equals 0. So we're trying to find the minimum for this function here. And so how do we formulate this? How do we solve this? We essentially take the first and the second terms of the Taylor series expansion for this function, and we get rid of the rest. Right? Again, so we can approximate G2 by taking the value of G2 at an operating point plus the first derivative times delta x1 plus the second derivative delta x1, going on and on and on. Now the fact that we have two variables here means that our first derivative, we have to actually consider the first derivative with respect to x1 and the first derivative with respect to x2. Then what's not shown here, the plus dot dot dot, that would be second derivative with respect to x1, second derivative with respect to x2, and you would keep moving on down the line. And so in order to get a perfect representation of this, you have to do an infinite number of derivatives. We're only going to use up until the first derivative. So there'll be three terms. There'll be the operating point, first derivative with respect to x1, first derivative with respect to x2. But we're not ever going to be using this in that form. We're going to be using it in this equation, in this matrix equation-based form here. And so using or implementing the Newton-Raphson method is mostly just, okay, boom, I know this is the form that I need, which is a little bit different than the Gauss-Seidel, right? With the Gauss-Seidel, you kind of have to formulate each bus's equation a little bit differently, depending on how many lines are connected to it and whether it's a PV bus or a PQ bus. But that doesn't come into play for Newton-Raphson. You have your Jacobian matrix. You need to go and define what all those values are, which after you take the derivatives, these will be expressions where you just have to plug in the values of x. So although you do have to take the derivative for each value of the Jacobian matrix, you don't have to take the derivative each iteration. You take the derivative once at the beginning, and then you just plug in values for each iteration. Same thing here, you plug in your values for your constraints, and then this is, if you think about this in an iterative fashion, right, this is the previous iteration, and then it gives you the next iteration, you plug it back in and go around and around. Last time, we had gone through this example number 3, so we've done this already, the simple non-power flow Newton-Raphson example. So non-AC example, and what we did was we had these two expressions, nonlinear, not really any good algebraic way to solve them, and we showed how to formulate the Jacobian matrix, and we did one iteration. This is several iterations done in MATLAB. The Newton-Raphson is a little bit It's a little bit harder for me to, do on the iPad and write out every single element. A lot of it is, there's a lot of values. So I think that using a computer and trying this in MATLAB is probably a better approach to learning it than trying to do it by hand. It's not a method that makes sense for doing by hand. Maybe for a very small system. Okay, so last time we didn't really get into the nuts and bolts of, so how do we apply the Newton-Raphson to a power problem? So G is simply going to be, for each bus in the system, we have our P injection minus the power flow from that bus. As you know, right, we expect when we get to the solution that those two values will be equal and this will be equal to 0. Again, conservation of power. The injected value should equal the flows going out along all the lines. We know all these values here. Voltage at bus I, voltage magnitude at bus I. GII bus, this is just the real part of YII bus, right? G is conductance, B is susceptance. So if you calculate your Y bus matrix, you can just pull out the real part of that element. Voltage magnitudes, Y bus, voltage angles, Y bus, etc. So none of these values are new to you. The form of it may look a little bit different. That's just because the variables are stated a little bit differently, but it's still, again, just the sum of VI minus VK over ZIK times VI. So it's just the calculation of the power flowing along all the different lines to the other buses. We're not going to go through the derivation of how to get this specific form right here. It's in the book if you want to take a look at it in Chapter 5. We're just going to go ahead and use it. But it's important to understand what the terms mean. This is essentially the self-admittance term. And then you have the term representing the power to the other buses. So one thing that we're going to have to do for Newton-Raphson is we're going to have to be able to take the derivative of these functions right here, which is really not that bad because, first off, when we're taking the derivative of the voltage, so our x's are going to be the voltage magnitudes and the voltage angles, right? Those are our different x's, x1, x2, x3. Taking derivative with respect to the voltage magnitudes is going to be easy, right? Because it's a coefficient, so you'll just knock it off, right? You'll just push it off the end. And then taking the derivative with respect to the angles will simply be, going to negative sign and going to cosine. So taking the derivatives is not going to require any math that you haven't done a bunch of times before. And the nice thing is, we'll see in a second, there's a form or a format that we're going to lay out. So you really don't even have to take the derivatives. What we're going to do is we're going to show you that the Jacobian matrix is made up of like these certain equations, and you can just plug them in. Now those are a result of taking the derivatives, but we're not going to do that specifically. So what is our system state? All the voltage angles and all the voltage magnitudes. It's a little bit different than the way that the Gauss-Seidel works, right? Because in the Gauss-Seidel, even though we said that the system state was the voltage angles and the voltage magnitudes, it was really the complex values together because we were considering them as one unit, right? We were updating both the voltage magnitude and the voltage angle at the same time. In the Newton-Raphson, it's going to be very separate. So for example, for the PV buses, let's say bus 2 is a PV bus. We know what the voltage magnitude is. It's going to be very easy for us to just completely cross that out of the setup. We're going to knock out the row that corresponds to V2, and we're going to knock out the row that corresponds to to Q2. And that'll be eliminated. And so this equation 240 is like sort of the most concise representation of what the Newton-Raphson update expression looks like. The next iteration of x, which is again the next iteration of all these values in here, is equal to negative times the inverse of the Jacobian matrix, which we haven't gone into too much detail. I mean, we know what that is in ideal terms. We haven't talked about the specific elements of it for the AC problem, times the constraint, which is going to be this guy up here. So all the different P's and all the different Q's. Remember that the dimensions are going to match up. So if you have 10 elements in the x vector, meaning you have theta 1, theta 2, theta 3, theta 4, theta 5, v1, v2, v3, v4, v5, the Jacobian matrix will be a 10 by 10 matrix, and this will also have 10 rows. Okay, there'll be P1, P2, P3, P4, P5, Q1, Q2, Q3, Q4, Q5, working all the way down. All right, and so here you can see sort of a blown up version of what it looks like, where they use the dot, dot, dot to sort of show the middle. So you have Q2, sorry, that should be theta 2, theta 3, dot, 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 theta n minus 1, theta n. Then it switches over to the V2, V3, dot, 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 all the way down to Vn. This is the same as this, except for the iteration number, and then you can see, right, the expression. So this expression is the exact same expression from that which was shown above. And we still haven't given the specifics on this Jacobian. So you can split this up into really two different halves. I mean, you can't split it up in terms of the calculation. You need to calculate everything all at once, but there's definitely two halves to this. All the P's go along with the deltas. All of the Q's go along with the V's. So let's say, for example, you end up with a problem where there's 3 thetas and 6 V's. That means you should have 3 equations that go along that are real power, and you should have 6 equations that are imaginary power or reactive power. Okay? That relationship is one that's going to be always present. V corresponds to Q, theta corresponds to P. And part of that goes back to this idea of the PV bus, right? Because every time we have a PV bus, that's going to eliminate a V, and it's going to eliminate a Q. So if this bus becomes a PV bus, this goes away. We no longer know the Q value, and that goes away, or the Q injection value. Okay. So here's where it starts to look a little bit dicey. So the Jacobian matrix. All that this shows is how to take the partial derivatives. The rho corresponds to the P or the Q value. So for example, these rows up here, P2, P3, P4, P5, Q2, Q3, Q4. Those rows are the same as these rows. P2, P3, P4, P5, Q2, Q3, Q4, Q5. Okay? And again, if you have 3 P's and 6 Q's, same thing you should see here. 3 rows of P, 6 rows of Q. The columns are the state variables that you're taking the derivative with respect to. So if you look up here, these are the columns. Theta 2, theta 3, boom, boom, boom. So when you set up the problem, the ordering is important. You can put them in any order you want to. If you want to, you can do V3, theta 2, V6, theta 5, I mean, whatever. It doesn't matter. Obviously, in most of the problems that we're going to do, we're going to have some sort of a numerical order because that just makes sense. 99% of the time, we're going to split up the thetas and the v's because that also makes sense. But if you want, I mean, it's really your call. You could just, mix them up if you wanted to. But the ordering that you set will determine what the composition of everything is. For these problems, normally we'll do the thetas first, we'll do the v's second, which means we'll be doing the p's on top and the q's on bottom. Now this is like a really, this is, when you look at the size of this system, this is beyond what we would probably do in this class. Because this would be, if you look at it, forget about the n for a second. Just imagine it being an 8 by 8 Jacobian matrix. Okay, so that would be the equivalent of a 5-bus system, right? Because you take away the infinite bus is not going to be represented, and so you have 4 thetas and 4 voltage magnitudes, which means 4 buses. So that's a pretty big system, especially for our purposes. Now, let's say if you cut this down to a 3-bus system, like the one that we did in the Gauss-Seidel example. 3-bus system, well, actually Gauss-Seidel was a 4-bus system, but let's say it's a 3-bus system. 3-bus system, one of them is a PV bus and one of them is a PQ bus. Then you only have 3 variables you're solving for, right? You're solving for the theta at bus 2, and you're solving for the voltage magnitude and the theta at bus 3. Okay? Which means now you've cut this matrix size down to just a 3 by 3. So the notes are showing worst case scenarios, larger matrix formulations, because you need a larger matrix to really see the patterns, right? If I did a 3 by 3, the patterns wouldn't be so evident. But we're not gonna, especially not for if you end up doing any of these problems by hand, which I don't know if you'll ever end up in this class doing a by hand Jacobian, a Newton-Raphson. It might all be computer based, but right, the sizes would be appropriate. You can split the Jacobian matrix up into these quadrants, assuming you order them correctly. Now, if you mix up the order and do theta 2, V3, and just whatever, then they won't be able to be, they won't have these quadrants. But you have your dp with respect to d theta. You have your dp with respect to dv, dq with respect to theta, dq with respect to v. You expect for these relationships to be stronger, okay? The relationship between p and theta is strong. The relationship between q and v is strong. And these, the off-diagonal submatrices, the values will be on average smaller. There's less of a correlation between those. Or you could say theta has less of an effect on q and v has less of an effect on p. All right, so now, if you look, we're just going to tell you exactly what the different values are going to be. Okay? So, let's say you will have a Newton-Raphson problem at some point. Okay? There's really only the final exam left. So, on the final exam, you'll have a Newton-Raphson problem. But as you see here, you don't even have to do the derivatives, okay? Because we've given you what those values are. You just have to know where to plug them in. The values are different. There's the diagonal values. There's the off-diagonal values, okay? So let's take a look at how these work. So there's 4 different types of derivatives that you have to deal with in the off diagonal. There's dp d theta, there's dq d theta, there's dp dv, and there's dq dv, right? Those are the 4 different types. And so let's say you have an off diagonal of dq2 dv3. That means all the i's will be 2's, all the k's will be 3. So all you have to do is plug in the different subscripts. And then, right, you know all these values. The v's and the thetas will either be the initial condition or whatever the previous value was, right? You're always going to have a running value of all the voltage magnitudes and all the voltage angles. Your Y-bus matrix should be defined, etc., etc. So without doing the derivative, the derivative's already done for you. You plug your values in here, and you have your off-diagonal values for the Jacobian matrix. Over here in the red, they're just trying to show that this equation is the same as this equation, except divided by vk and multiplied by -1. And they're trying to show that this equation is the same as this, except, again, divided by vk and just divided by vk, right? That's the only reason why they use those alphas and betas in there, is just to show the relationship between them. So now we know how to plug in the values of the off diagonals for the Jacobian matrix. Now the diagonals, again, 4 different types. On the diagonal, we're going to have dp d theta, dq d theta, dp dv, dq dv. Same different things. And that's it. Just plug in the values that you know for these. Here you do have the sum. These 2 expressions have a sum in them. And so k to n, you're going to be summing for all the different combinations where a line exists, right? Y bus ik will be 0 if there's no line between buses I and k. So like, let's say there's 5 buses, right? So you could have as many as 5 terms here in this for this sum. But if there's only a line, and we'll say we're doing it for bus 2. If there's only a line between buses 2 and 3 and 2 and 5, then 2, 1 will be 0. 2, 2, well, you have to consider that. 2, 3 will have something. 2, 4 will be 0. You get what I'm saying. The Y buses will, the 0 values will knock some things out. And then, so how do we define the Jacobian? You end up with something like this. So again, the diagonals are those which fall right on the diagonal here. And everything else is an off diagonal. And if you think about the example of doing a 3 by 3, then you can see it becomes a lot more manageable. Your matrix shrinks to something like that. And that's the example that we're going to do. Now, how do we treat PV buses, voltage controlled buses? So let's say bus 3 is a PV bus. Okay? That's it. All you got to do, knock this out, knock this out, knock this out. Delete it from the array. Then you go to the Jacobian matrix down here. Knock out the whole row that has to do with Q3, and knock out the whole column that has to do with V3, and the whole thing shrinks. So if you originally had a 4 by 4, it shrinks down to a 3 by 3. And there's none of the nonsense that we had in the Gauss-Seidel where we updated it, we took the angle only, and we replaced the V magnitude. We're not even, V magnitude is not going to even be a part of the analysis the same way that the voltage is for the infinite bus. They're not part of it. Yeah?
So it's just to reiterate, if there's a PV bus, ignore the corresponding V row and the Q column?
It's actually the Q row and the V column, yeah, because the only column you'll be eliminating will be a column within the Jacobian matrix. And then the Jacobian matrix, the thetas and the V's dictate the columns.
Okay.
Right? It's a V3, 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 V3.
So what's the other matrix again?
There's only one matrix. There's multiple arrays. Like the other ones.
What's the other array above? Now when you get rid of what?
You get so this is the Jacobian matrix right here. I just didn't have room to put it in there. So again, if we're considering bus 3 as the PV bus, V3 goes away, Q3 goes away, V3 goes away. Right? V3, Q3, V3. Then down here, anything associated with Q3 goes away. That's one entire row. And anything associated with V3, that column goes away. So it's just all the Q3s and all the, yeah. You shouldn't have a Q3 or a V3 show up in these arrays or matrices. And so actually here's an example of eliminating it. And here's a more reasonably sized example. Now you can see when you start to reduce it down to the sizes that we're going to be working with, now it doesn't look as bad. So this is an example of a 3-bus system, 2 non-infinite buses. Our bus number 2 in this case is the PV bus. And so that goes away, and that goes away, and you just collapse the whole thing, and you end up with a 3 by 3. And so hopefully now, right, that doesn't seem as bad as it would be otherwise.
So if you're given a 2-bus system and one of, or 3-bus system, one of them an infinite bus and then one PV, you're really just working with one. But how would you?
Well, you still have to solve the theta for that bus. Right? So the number of state variables, going back to the very beginning, the number of state variables that you have to solve for is the number of buses times 2. Right? Minus 2 for the infinite bus, because we're not solving those, and minus 1 for each PV bus. Right? So if you start off with this, if we look at this example here, 3-bus system times 2, so that's 6. Okay? We knock off the 2 for the infinite bus, which leaves us with 4. And then, since this one is a PV bus, we'll knock off 1 more, and that leaves us with 3, which is the theta for the PV bus and then for the PQ bus. If we also make bus 3 a PV bus, then we knock off 1 more, which means that this row and this column would disappear, and that leaves you with 2 values to solve for. So, going back to the beginning of the chapter, when we did that calculation of, okay, how many state values should we have, how many constraints should we have, that's not a trivial thing. It really does help with this because you know how big your array should be, you know how big your matrices should be, and that's a huge help because it's already, as you can see, a little bit confusing because you have so many different values to work with. So if you can have a guide, that's advantageous. But on the bright side, once you have all this set up, doing the iterations is easy, right? You have your Jacobian matrix defined, you have the different arrays defined, and then you're just plugging in the values and running the same thing over and over again. So let's take a look at an example. So we're actually going to do a very similar example, but we're going to do it using using the Newton-Raphson. So where? All right, so all right, so let's go ahead and jump in. So okay, 4-bus Newton-Raphson power flow. I'm going to skip some parts of it that we did for the Gauss. I'm not going to go through and spend a lot of time recalculating the Y-bus matrix. I think that we spent a lot of time on that before. So I'm just going to go ahead and give us what the Y-bus matrix is going to be. And we'll try to skip straight to the chase, which is like the actual Newton-Raphson, part of this thing. So, what's the system information? I think it's exactly the same as the previous, but let's go ahead and just show it one more time. So table 9.3 shows that for buses 1, 2, 3, and 4, we have P gen in megawatts. We have a Q gen in megawatts or megavar value. We have a P load in megawatts, and we have a Q load in megavar. We'll have a nominal voltage. And then lastly, we'll have a bus type. So, for a lot of the people who aren't here right now, I think that they're going to even have trouble defining the problem, because it's a very specific way that you have to do this, right? There's more information going to be given here than you need. Some of this information is not useful. So for the so let me start off by defining the types. So they say that this is an infinite bus, load bus, PV bus. So I'll use these names. So PQ bus, and PV bus. All right. And that's synonymous with load bus, synonymous with load bus. That's synonymous with generator, or what we call voltage controlled bus. Okay? Those names are all synonymous. Okay. So we don't have any generation or a known generation value for bus number 1. There's no generation at bus number 2. There's no generation at bus number 3. At bus number 4, we have 318 megawatts, and the Q is unknown. There's load values 50, 170, 200, 80, 30.99, 105.35, 123.9, picking some really weird values here, 0.94, and 49.58, very specific. Our nominal voltage is essentially going to be 1 with an angle of 0 for all of the buses. This is the same as the previous definition, except this one last here. The last one is 1.02 with an angle of 0. Okay, so taking a look at this and circling the values that we need, right? An important first step in this analysis. So we need all the bus types. I mean, that's... What's going on here? That's a given. We need to know the bus types. Then, for our infinite bus, the only value we need is that. For our PQ bus, the values that we need are these two. For our PQ bus, again, the values that we need are these two. For our PV bus, we need this, and we need this. The rest of it, not really going to play a strong role, any role, in the analysis that we're going to do. We can use the nominal V's as the initial condition, which we will, but we also could use a different value. So Y-bus matrix, same process that we went through for the Gauss-Seidel. I think we end up with the same matrix. And I'm just going to go ahead and write that out. So give me a second. I would skip the step of writing it out, but then I think it would be really hard for us to refer back and forth each time. So that's a good question. We can ask that. Let's ask that question. How many state variables are we solving for? Well, actually, no. The admittance matrix is not related to that. I apologize. That's the Jacobian matrix. The admittance matrix will be related to the number of buses. So it'll be a 4x4. Yeah. I was skipping ahead. But we can still ask ourselves the question. Let's ask ourselves the question of how big the Jacobian matrix will be. So how many states are we solving for? 5. So yeah, 5x5 Jacobian matrix. This is still a little bit larger of a problem than I would preferably like to ask you on a quiz or an exam. I think for the exam, I would limit it to 3 bus. Hopefully with only 3 variables to solve for, which would make your Jacobian much smaller. And we're not going to get into anything about matrix inversion. Sometimes power systems courses will, like when I took this as a graduate student, the most difficult part of this problem is inverting the matrix when you talk about it from the computer end, and that's what takes up the most time. So a lot of courses will go into faster ways to invert matrices, LU decomposition and all that type of stuff, but we're not gonna have a chance. So we're just going to be going MATLAB or calculator to the -1 and let it handle it. But you'll see, if you try to run, because I have the MATLAB code to do the Newton-Raphson for this problem, even for this 5x5 matrix, you'll see it's not like some other problems we've gone through. It takes time for it to calculate. It will, it's not going to take minutes because it's still just a 5x5, but it'll take a couple seconds. Matrix inversion is one of the most time-consuming mathematical operations, basic mathematical operations out there. Again, remember you expect your elements along the diagonal. Don't forget the basic rules of these Y-bus matrices. You expect the elements on the diagonal to be positive. Now, that doesn't necessarily apply to the inductive part because capacitors and inductances that can take on either sign. But for the resistive part, the resistance will always be positive, so you can tell there. And I'm not going to rewrite the symmetrical elements because we know that they'll be the same as the flip of the indices. Okay, so that's our Y-bus matrix. All right, second step. So we already did this. We defined the size of the Jacobian matrix. We said that's going to be a 5 by 5. So Jacobian will be a 5 by 5. Okay, let's define what the x's are going to be. All right, we said we're normally going to order it thetas, then v's. Okay. For bus 1, we don't have anything. For bus 2, we'll have a theta. For bus 3, we'll have a theta. For bus 4, we'll have a theta. So we'll have thetas that we have to solve for all of those. So theta 2, theta 3, theta 4. The one that we don't have to solve a V for is the fourth one. So that means we'll have a V2 and a V3. And then if you want to translate that to the G's, okay, you'll see that we'll be worried about the delta P2, the mismatch between the injection and the flow for P2, the delta P3, the delta P4, the delta Q2, and the delta Q3. So that tells us, yeah.
Do the X row or column.
Mm.
I'm kind of seeing how you're determining it's theta 2, theta 3, theta 4.
Sure, let's step back. That's a very important question. Okay. So, going downward from top to bottom. The types of buses. So for infinite bus, do we need to calculate theta 2? No, that's already known. For a PQ bus, we need to calculate both the values. So we will need to calculate theta 2 because that's a PQ bus. Essentially, you'll always need to calculate all the thetas except for the infinite bus because we don't have the equivalent of like a theta Q bus. You know what I'm talking about? We have a PV bus. We don't have the opposite version of it, right? So you'll always have to calculate all the thetas except for the infinite bus. So we know we need theta 2, theta 3, theta 4. Really the only question is, where are the V's going to be missing? So instead of it being V2, V3, V4, the fourth bus is a PV bus, so we pull that guy out. So that's the easiest way to think about it. Why is this thing having a heart attack here?
And you chose V2, V3 because it was PQ buses?
Yes, exactly. So, Avengers Endgame, huh? We won't give spoilers. I mean,
When did you see it?
I saw it on Friday.
Friday.
I mean, when Ant-Man died, it was tragic, but not as good as Infinity War. That was my opinion. What are you going to do? Should I hit cancel? I don't even know what it's doing. Cancel? Oh, okay. Well, that's easy. I don't know. But see, now it's not. Now it won't move.
That's fine. Still be Rapson.
Okay. Well, you can copy it. If I do this, weird. There we go. Nope. All right. All right. We're back. Okay. So, those are the values. Okay. Everyone got copied? What they need to copy? So step 3. Now, let's go through and define all the elements of G, because we're going to need actual equations that we're going to plug values into in terms of your thetas and your V's. So if we go back up here, okay, we know first off, as we said already, just above, we know that G is going to have 5 elements. It's going to be mismatch P2, it's going to be mismatch P3, it's going to be mismatch P4, it's going to be mismatch Q2, and it's going to be mismatch Q3. So that's what it's going to look like. But now what is it actually going to look like? So it's all going to be based off of this equation here. This. Okay? So for the first one, and let's just go ahead and we'll say it, and then we'll write it down. Okay. So the first one we're doing is P2. So that means it'll be P injection 2 minus V2 squared G22, so the real part of the 2 element of the Y bus, plus, now we have the sum. Bus number 2 is connected, if I remember correctly, to bus 1 and, because 1, 2, 3, 4. So it's connected to bus 1, it's connected to bus 4. So that means that we'll have V2, V1, Y21, cosine theta 2 minus theta 1 minus the angle of Y21 bus. There'll be no 2, 3 element, so that'll be gone. There'll be no 2, 2 element because we say K is not equal to I. And then there'll be a 2, 4 element where we have 2, 4, 2, 4, 2, 4, 2, 4. Okay, so again, when you have these sums, you know how many components there should be based on how many lines there is connected to that bus. So let's go ahead and now and write that out. Hopefully I remembered correctly what the topology looked like. And all this is in the notes done already. I'm just doing it by hand because I think that, well, it's a lot. So not explaining it by step is tough. Okay, so before I start writing it down, I was right. So you have 2, 1, and you have 2, 4, and that's the only thing that we have to worry about. Okay, so we got P2 injection minus V2 squared B22 bus. And then here is the first of the 2 elements in the sum. V2, V1, Y21 bus. Whoops. Times sine theta 2, theta 1, minus the angle of Y21 bus. Okay, and so this represents line 1 to 2, or 2 to 1, however you want to state it. Yes?
I'm confused now. Isn't this the equation for the delta Q?
Sorry.
Oh, and then that's
It should be G. You know what? If you look at the order that I did it in the notes, I had the P's on top, or the Q's on top, so I'm like, I'm reading from the top row when I should be reading from the third row. Yeah, it should be G, 2, 2. And cosine. I gotta make sure I'm reading from the right row. Okay, then there's one more element, which is going to be for the 2, 4. So V2, V4, Y24 bus times cosine of theta 2 minus theta 4 minus Y24 bus. And then that's it for that element. We'll do like 2 or 3 of them, and then I'll sort of put X's, and you can refer to the notes to see the other ones.
And then there should also only be one negative sign now. At the very start.
Yes, I'm sorry. Okay. Next time I'm definitely going to read the right row. Okay. So let's try one more P, and then we'll do one Q, and then we'll skip to the next step. Okay. So let's try P3. And now that we have the model right above it, it'll be easy. So we have V3 squared. G33 bus. You see, again, like, once you do the first one, now doing the second, third, you start to roll, and it gets a little bit easier. That's the thing about the Newton-Raphson is, once you get used to the pattern of the way things are going, it's like it starts off slowly, and then you're like, okay, this is the same thing, this is the same thing, this is just changing the numbers over and over again. Bus 3 is connected, so it's 1, 2, 3, 4, so it's connected to bus 1, it's connected to bus 4. So the first one we'll have is V3, V1, Y31 bus, cosine theta 3 minus theta 1, angle of Y31 bus, okay, plus V3, V4, Y34 bus. Let me make sure that connection's right. Yeah, Y34. Okay, cosine of theta 3 minus theta 4 minus the angle of Y34 bus. Okay, now let's skip P4. And now let's go down to Q2. So Q2 injection minus a negative V2 squared B22 bus. And we can model the structure of this one really heavily off of the first equation. Plus V2 V1 Y21 bus. Sine theta 2 minus theta 1 minus angle of Y21 bus plus V2 V4 Y24 bus sine theta 2 minus theta 4 minus Y24 bus angle. And then you repeat the same thing for the last one, and you got your answer. So for these, I'll say refer to the PDF if you want to get the exact values. But it's the same thing over and over again. So even though this is a little bit of a larger example, right, it only took us what? with me doing it in front of everybody and trying to explain it, it was like, what, 3 or 4 minutes to write this part out. So, not too bad. The numerical values, so the next step, now here's where the breakdown between doing things in the calculator or doing it by hand versus doing it on the computer becomes really evident, because there's a lot of places to mess up putting the numbers in just because there's so many numbers. And one thing that we haven't explicitly stated, although I should have said, is, let me put it in here as a mini step. We need initial conditions, so we can assume a flat start. Yeah?
I just want to make sure I understand the PV bus correctly.
Mm.
The injection for P4 would be P-gen minus P-load, correct?
Yeah,
Okay.
we can actually stick those values in here. So let me do those. Let's write them in green. So the P injections would be, so negligible, minus 170, minus 200. So what's 318 minus 80?
238.
Oh, well, yeah, it's 238. Same from last time. 238. Our Q injections are going to be your minus 30.9. Well, it doesn't matter for the infinite bus. Minus 105, minus 123, and then doesn't matter for the PV bus down there.
I understand all those besides the 238.
It's 318 minus 80. The injection will always be the generation minus the load, because the injection is assumed to be a positive value, or assumed to be referenced going into the bus. So generation is positive, load is negative. And so fill in the numerical values. I'm just going to go ahead and give what the numerical values are. So it gives us minus 0.45, minus 0.83, minus 1.59. Actually, I have to mix up this order because mine's ordered differently. So for us, it's going to be minus 1.93. So just like the way that we did it in the Gauss, Seidel, everything's going to be in per unit. The only conversion that the only value that wasn't given to you in per unit is the injections. So you'll have to do, again, like your, 170 divided by 100 MVA, 200 divided by 100 MVA, it'll give you